This is our second video on structure and bonding, module 1. I'm just going to make a brief mention of the most common elements used in organic chemistry. These are elements of life, when you think about it that way. And for the most part, the bonding theory that we're going to talk about today applies to all of these. Phosphorus and sulfur can have more than an octet, so there's more to it for those, but for the most part applies to all of these. So if you recall the shapes of s orbitals and p orbitals from general chemistry and how electrons fill orbitals, the p orbitals are oriented along xyz axes. They're dumbbell shaped, while s orbitals are spherical. So if you look at the periodic table, this number 6 is technically 6 protons, right? But for a neutral atom, it equals the number of electrons in a neutral atom. Since they're balanced, plus and minus. So the 6 electrons as they fill the shells in the old methods, 1s2, 2s2, 2p2 is carbon. So the problem is if you try to predict bonding directly from this. Let's draw, I already have drawn the 1s orbital interior, the 2s spherical orbital larger and outside of that, each having 2 electrons in them, like it says over here, and then the 3p orbitals oriented along xyz axes, and we fill the remaining 2 electrons in the 2p orbitals here and here, leaving an empty pz orbital. And so this doesn't predict the known bonding of carbon. And in fact, it would predict things that don't typically exist or exist very easily. For example, it would predict, in this case, a carbon with, say, 2 hydrogens bonded and a lone pair, which I will say can exist, but it doesn't exist as derived directly from this. And it's called a carbene, by the way, to digress. But it's very reactive and pretty much unstable. So the main thing is this old bonding theory doesn't predict the real bonding situation. So we need a new theory. So in science, when something fails to predict, we need to move on. And this brings on hybridization theory. Hybrids or hybrid orbitals. And what this really amounts to is a way of rearranging electrons in space so as to have predictability. And it works really, really well. So back to the atomic orbitals here, 1s, 2s, py, pxyz. If we take just these, leaving the interior deeply buried 1s2 electrons alone, and we hybridize the s and all 3p orbitals. So the important thing to remember here is we're taking 4 atomic orbitals, merging them, creating hybrid orbitals, but if we start with 4 atomic orbitals, we have to end up with 4 hybrid orbitals. You can't lose orbitals. So we do, in fact, end up then with 4 sp3 hybrid orbitals, and this stays unchanged, the 1s. So we almost usually forget about that. So carbon is technically, to be completely correct, 1s2 sp3 4. Where each of these new shaped orbitals are sp3 orbitals. They according to VSEPR, will repel each other and get as far apart as possible. And that's what happens in this picture right here. All 4 sp3 orbitals will arrange themselves in what's called a tetrahedron. So methane is tetrahedral in geometry. And I've drawn it like this, but another way of drawing it is like this to show the orbitals. And again, sp3, 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 each bonded to a hydrogen 1s, which is all a hydrogen atom is, by the way. A hydrogen atom is just a proton and an electron, a 1s, 1 orbital, essentially. I guess I already had that written here. Another way to show three-dimensionality is here, and that's with the wedge and the hash mark symbolism, and this is back and forward. I would urge you to try and start making models and seeing how line drawings like this relate to the models you're building. Okay, so we have some dramatic footage of all this. First off is the formation of the hybrid orbitals. So just another way of looking at it, there's the XYZ axes, there's the s orbital, and now come all 3 p orbitals that originally are aligned along the axes, right? But now as they hybridize, like a donkey and a horse hybridizing into a mule, and you saw the picture, and now you have the 4 sp3 orbitals, but now they're not on XYZ axes exclusively, because they have to get as far apart as possible by repulsion, electron repulsion. When we see here's another view of it that shows some more details. So there's the bonding to create the molecule methane with the 4 hydrogen atoms coming in and bonding to the sp3 orbitals. So methane's a tetrahedral molecule. That can be shown experimentally. Another way to look at it is actually a really important concept, the electron cloud view. Let's take another quick look at that. So there's the sp3 orbitals, the hydrogens coming in, and you're looking down the z-axis. Okay, and then the electron cloud and electron density, pause that. So notice the electron density is greatest where there's red. That's going to really be aligned basically with where the bonds are, not around the nuclei. There's lower electron density along the points where the hydrogen atoms are. And then on the interior, then you see the tetrahedral shape in the interior. So, finally, we can apply this to a molecule like oxygen. Oxygen is number 8 in the periodic table. Uh, 2, 4, 6, 8. The 1s2 electrons buried deep. We hybridize the same s and 3p orbitals. We get the 4 sp3 orbitals here. And if we fill electrons in order, 1, 2, 3, 4, 5, 6, 7, 8 is in the 1s2, the last 2. We hybridize these. We get 4 sp3 orbitals in a tetrahedron. The only difference is now oxygen can bond in this way, like in water. So this is a water molecule. Here we have a covalent bond and a covalent bond with the unpaired sp3 orbital electrons, and the other ones that are paired up are in lone pairs. So the bonding of oxygen is easily predicted by hybridization theory as well. The 1s2 is not shown. And so we have an accurate picture of water. And as you recall, maybe from general chemistry, it's not quite it's tetrahedral, but it's bent downward more. These two bonds are repelled a little bit more than your exact tetrahedron by the non-bonding or lone pair electrons. They tend to have a little slightly more effect than bonding electrons in repelling. Okay. Hopefully that's all review. The main conclusion here is that structure is related to function in science. Chemistry is no exception. So if you understand the structure, you can understand the behavior.